Happy morning, dear friends. Here's yours, Dr. Rajanta. Welcome to Demystify with Ajay. Dear friends, today we are going to discuss a lot related to vectors, matrix, linear algebra, matrix inverse, determinants, of course, a lot and lot. Yeah, without delay, let me just get into the session. Dear friends, actually, previous session we have just discussed about the vector. So a vector is a mathematical entity used to represent physical quantities that have both a magnitude and directions, and it's a fundamental tool for solving engineering and machine learning problems. So or matrix which are used to represent vector transformations among other applicants. So let me just have a small vectors also here. I just want to show you a small things. If I just want to make use of an vector like this, so here I have already given you something as like 1 2 3 4 and 5 6. Let I just take the same example here. How the exact matrix it would be shown is like this. So this is how. And imagine that you need to create this exact matrix, and with NumPy you can also use np.array to create this, and providing a nested list containing the elements of each row of matrix. Kindly just have a note of it. So let me just make use of it. So kindly just see here, this is what by using a NumPy we are just imported, and here it is our matrix. So when on just making it, dear friends, actually see this NumPy provides several functions to facilitate working with vectors and matrix computations. You can find more information how to use NumPy to represent vectors and matrices and perform operations with them in this previous sessions also we have just discussed, and here we are just going towards the linear and linear algebra. And before starting it towards linear algebra, I just want to let you know one small thing, dear friends. A linear system, or more precisely a system of linear equation, is a set of equations linearly relating to a set of variables. Let I just again give you a small example about that. So kindly just see here, I just give a small example. So we are going to have one particular thing. So 3x1 plus 2x2 is equal to 12, and 2x1 minus 1x2 is equal to 1. So of course this is a linear system relating to variables x1 and x2. And here you have two equations involving two variables. In order to have a linear system, the values that multiply the variable x1 and x2 must be constant, like the one in which we have just seen here. And it's common to write linear system using matrix and vectors. So for an example, you can write this exact equation as a matrix product. How you are just going to make it is as like, so 3, 2 and 2 minus 1. This is how the exact thing, and we are just going to product it with the matrix. And kindly observe, dear friends, and this one would be our matrix A, and this is X and towards the B. So comparing the matrix product from with this original system, okay, you can notice that the element of matrix A corresponding to the coefficient that multiply x1 and x2. So beside that, the values in that right hand side which we have, of course, original equation now make up as like a vector B. And linear algebra is a mathematical discipline that deals with vectors, matrices and vector spaces, and of course linear transformation more generally. By using linear algebra concepts, it's possible to build algorithm to perform computations for several applications involving, including solving a linear system. So where there are just 2 or 3 equations and variables, it's feasible to perform the calculation manually, combine the equation and find the values for the vectors or the variables. However, in real world applications, the number of equations can be very large, making it infeasible to do calculations manually. So that's precisely when linear algebra concepts and algorithms come handy. Okay, allowing you to develop usable applications for engineering and machine learning example. Okay, and yeah, of course, dear friends, in working with this linear systems, mainly by using this Python, yeah, we are going to make use of the SciPy, of course, with the module with including linear algebra, and you have seen how to solve linear system using this SciPy. We are just going to discuss more the thing. But when on comparing towards this, kindly just observe, dear friends, here we are going to make use of that SciPy, that is importing towards linear algebra. NumPy also includes some tools for working with linear algebra applications, as like numpy.ling, that is which we just say linear algebra model. However, unless you don't want to add SciPy as a dependency to your projects, it's typically better to use SciPy.linear algebra. See, this SciPy dot linear algebra, which is always compiled with the support for basic linear algebra subprograms and linear algebra packages. So, which are libraries including routine for performing numerical operations in an optimized way. So, for rather than this NumPy, which that uses of this basic linear algebra subprograms and linear algebra packages, that is optional. So, thus depending on how you install NumPy or this SciPy, and mainly using this linear algebra functions, might be faster than the one which you just make it your NumPy. Okay, so all in all, considering that scientific and technical applications generally don't have restrictions regarding dependency, it's generally a good idea to install SciPy and use SciPy dot linear algebra instead of NumPy under linear algebra. Okay, so yeah, let me just go with this the same equations where we are just going to discuss with that one. Yeah, let me just have a quickly think. Yeah, dear friends, we have 3x1 and plus 2x2 is equal to 12, and 2x1 minus 1x2 is equal to 1. Of course, considering the same equation, that is the system, yeah, in order to use this SciPy linear algebra, the solving, okay, so you need to write it into the matrix product. So here also we have just done it in the matrix product. Okay, so notice that you have arrive at the original equation of the system after calculating the matrix product. So the input that this SciPy dot linear algebra expects are the matrix and the vectors, so which you can define using NumPy arrays. Okay, so here, yeah, I'm just going to make it using a NumPy array. So this is what the A matrix and towards the B, and kindly just see this is the according to the equation. And yeah, when we just have see this exact the first line, of course, we have done with the SciPy along with the linear algebra, and here we have the coefficient of a, b, and towards the x. And yeah, let me just create the independent terms vectors by using this NumPy array. We have done it. and to make it as a column with the 2 lines, we have just done this reshape also. And last but not least, yeah, we have given this linear algebra solve of a comma b, actually it to solve the linear system categorized by a and b with the result stored in x, so which is going to be executed, and kindly just observe. So note that the exact return, this exact solve function return the solution with floating point components, even though all the elements of the original array are integer. And if you replace this, x1 is equal to 2 and x2 is equal to 3 in this original equation, then you can verify that yeah, it is a solution to the system. Okay, so yeah, dear friends, of course, let me just make use of something in a practical manner also. Let me just apply here. I have just given one more equation. Okay, so here I just give you one small thing. So let me build a mealing plan here. I just want to make one plan here. Vitamin A of, so actually here I just want to make a mixed different foods in order to get a balanced diet. Okay, so here let I just have a vitamin A. So 170 units of vitamin A and 180 units of vitamin B and 140 units of vitamin C, 180 units of vitamin D and 350 units of vitamin E. And of course, what we are going to have it is, of course, this is the exact task, and to find the quantities of each different food in order to obtain the specified amount of necessary vitamins. Okay, so let me just have it in a table manner. Okay, so I just give this under a table manner. So here we have the food, and this is vitamin A, vitamin B, vitamin C, vitamin D, and towards vitamin E. Okay, so let I just have, this is food 1, 2, 3, 4 and 5. And what are all the vitamins this food 1 has is 1 units of vitamin A, 10 units of vitamin B, and here I just specify some data related towards the food. So kindly just observe, this is just a sample. And I'm just giving us like a data. So when we just, okay, so here it is the data. Okay, so here let I just give a small thing here. This is what our task we have to make use of it. So with this meal plan, we want to identify so which food it would consist. So by denoting, for an example, if we just specify one thing. So see here, if we are having food 1 as x1 and so on, and considering that you are going to have a mix of x1 units of food 1, x2 units of food 2 and so on, you can also write anything as like an expression. Okay, so here if I just have, of course, our task, it is vitamin A. Here I just have a look. So this is vitamin A, it is 170 unit. So in such a case, how can I just specify? That is x1 plus 9x2 plus 2x3 plus x4 plus x5 is equal to 170. And in such a case, the same thing, what is the vitamin B? Yeah, it is 180 of vitamin B. Okay, so here we just need as like 180 of vitamin B and 140 of vitamin C and 180 of vitamin D and lastly 350 of vitamin E. Dear friends, actually considering that a balanced diet should include all these functionalities as like 170 units of vitamin A, and you can also use this data from here Okay, and we have just calculated it as like one particular equation. And yeah, dear friends, repeating all these things towards the same, what we just get, yeah, we have to specify as like 10x1. Let I just make it for B. Okay, 10x1, 1x2 plus 2x3 plus x4 plus x5, which is equal to 180. In such a case, yeah, we have to produce for vitamin B, C, D and E, and yeah, let we just have something as like an linear system. And when the same thing, if we just go towards the coefficient, okay, and if I'm not wrong, I just have a coefficient like this. Okay, I just have this transpose in the manner so that I can just get the exact matrix. 1 second, dear friends. So this is watch. So 10, 1, 2, 1, 1, 1, 0, 5. Yeah, exactly 1, 0, 5, 5, 1, 1 and 2, 1, 1, 2, 9. Kindly just observe. I'm just writing this towards in this manner here. Okay, so 2, 1, 2. 13 and 2, and of course we have our matrix as like x1, x2, x3, x4 and x5, and yeah, of course we know the exact units as like 170, 180, 140, 180, and last but not least it is 350. So this is how our vectors. Okay, yeah, let me just now just finding this out, let me just go for the quantiles from x1 to x5 by applying here. So this is how the exact expression is available. So I have just already given here. And yeah, dear friends, kindly observe how this is expressed. So here by using already we have included numpy, and of course for this linear algebra we have used from SciPy, that is already has been imported previously. Okay, for this issue, yeah, we have created a coefficient matrix by using numpy array, calling it as like A, the variable, and creating an independent terms vectors as a numpy array, calling it as like B. Okay, so to make the column vectors with 5 elements, we have just used as like reshape, and here this one I just execute it. So we just got A and B. And dear friends, by using the inverse things, we are going to obtain the inverse of matrix A, and by using the operator, that is this at operator, yeah, kindly just observe, it is used to perform the matrix product in order to solve the linear system categorized by A and B. So now you can just store the result into the X. So let me just see what is the X has. Superb. So now you get exactly the same solution as the one provided by this SciPy, by using this linear algebra and using the solve functionality. See, because the system has a unique solutions, na? So the determinant of here what we just got, it is how from this is concluded it is. See, actually it just indicates that balanced diet should include 10 units of food 1, 10 units of food 2, 20 units of food 3 and 20 units of food 4 and 10 units of food 5. That is how here we just have the conclusion of this final functionality. So this is how you can just make use of it. And yeah, dear friends, when I'm just speaking on towards the determinant, Yeah, of course, a determinant of matrix A must be different from 0, which I have already specified. And you can also confirm that it is by calculating it by using this deter. So this is the exact function. And yeah, of course, this is also from SkyPy linear algebra module. And kindly just observe here, yeah, it should not be 0. Yeah, as expected, the determinant is not 0. And yeah, I have already specified you, dear friends, a determinant is a number that is calculating using the matrix of coefficient that tells you if there's a solution for the system or not, because you will be using SkyPy linear algebra to calculate it. You don't need to care much about the details on how to make the calculation. However, but anyhow, I just let you know one thing. See, if the determinant of a coefficient matrix of a linear system is different from 0, then you can say the system has unique solution. If the determinant of the coefficient matrix of a linear system is equal to 0, then the system may have either 0 solution or an infinite number of solution. Okay, so kindly have a note. So, and yeah, and here I have also given one more thing. See, as expected, the determinant is not 0. Okay, so that indicates that the inverse of A, that is denoted as like how we just usually denote it. Once again, I just scroll above. Yeah, of course, we just specify as like A inverse. This is how we usually used to. And here, this can be easily calculated by using inverse of A. And exists, so the system has a unique solution. And dear friends, this A inverse is a square matrix with the same dimension as A. So the product of A inverse and A result in an identity matrix. And let me just see what is there in this equation. So I just want to know what is A. Okay, so this is what the A inverse. Okay, so now that you know that the basic of using matrix inverse and determinant, so now let me just make use of this by using these tools. Let me just go to find the coefficient of polynomial. Now, dear friends, actually, you can use linear system to calculate polynomial coefficient, so that these polynomials include some specific points. See, for an example, considering a 2-degree polynomial, if I just specify anything as like a 2-degree polynomial, let me just have P of x. So let me just have y is equal to P of x. Here a0, a1 x plus a2 x square. So here recall that when you plot a 2nd-degree polynomial, you get a parabola. So which will be different depending on the coefficient. This is a0, a1 and a2. Okay. So considering these different points, let me just end up with a system or with having something as like an 3 equations. Okay, I just want to give something as like 3 equations. So so by using here I have already given some points. So with the same, I just give some 3 equation, that is a0 minus a1 plus a2 is equal to 5, and a0, sorry, here it is plus only, and plus 2a1 plus 4a2, which is equal to 13, and a0 plus 3a1 plus 9a2, which is equal to 25. So that is what here I have just this exact equations. Yeah. Let me just check if this system has a unique solution, and yeah, you can calculate the determinant of this coefficient matrix and check if it is not 0. And yeah, of course, let me just calculate this towards the functionality by a matrix formation. So here I have just already given the same thing. So yeah, this is 1 1 1, which we have already specified a0 plus a1 plus a2, and the equation output for B, here it is. Okay, so yeah, here it is an A matrix. Let I execute it, and we have the B vectors also. And dear friends, we are here calculating the equations by making it as inverse. Okay, so inverse of this functionality, and this actually, it's worth nothing that the existence of the solutions only depends on A, because the value of the determinant is not 0. You can be sure that there's a unique solution for the system. You can also use this by solving it by inverse of A at B. Okay, so let me just see what is the A value. So 1, 2 and 2. So in such a case, here what the resultant specifies? What the resultant specifies? Of course, A0 is 1, A1 is 2 and A2 is 2. Is the solution of the system. So in other words, the polynomial that includes the point here, let me just have, how come this one? 1 and 5, and here it is 2 and 13, and last one it is 2 and 25. So if you look carefully at these numbers, yeah, you will notice that the second and third point consider x is equal to 2 and different values for y, so which makes it impossible to find a functions that includes both the points. Okay, so now let me just make once again. So to confirm this system does not present a unique solution. You can calculate the determinant of the coefficient matrix by using this determinant. So let I just make use the same thing here. I'm just going to specify it as like 1 to 4, and here also it is 1 to 4. Okay, so with this, let me just check what would be the coefficient. Okay. So you may notice that the value of the determinant is, of course, here we are getting it is in negative. See, this also means that the inverse of the coefficient matrix doesn't exist. In another word, the coefficient matrix is singular. The coefficient matrix is singular. See, depending on your computer architecture, you may get a very small number instead of 0. This happens due to the numerical algorithm that determines users to calculate the determinant in these algorithms. So numeric precision errors make this result not exactly equal to 0. Okay, so in general, whenever you come across a tiny number, you can conclude that the system does not have a unique solutions. Okay, so yeah, dear friends, let me just make use of this, and let I just have it in such a manner. So here, how the exact equation is. Of course, we just getting an error. So kindly just observe what is the error. Yeah, it is a linear algebra error specifying it as like a singular matrix. See, because the system has no solution, you get an exception telling you that the coefficient matrix is singular. When the system has more than one solution, you will come across a similar result. Okay, so the value of the determinant of the coefficient matrix will be 0 or very small, including that the coefficient matrix again is as singular. Okay, now how we can resolve it. See, dear friends, usually when you are trying to interpolate polynomial, you are not interested in a precision fit. You are just looking for a solution that approximates the point, providing the minimum error possible. Okay, so this is generally the case when you are working with real world data. So usually it includes some noise caused by error that occur in the collecting process. So like imprecisions or malfunctions in sensors and types when users are inputting data manually. So using the least square method, you can find a solution for the interpolation of a polynomial even when the coefficient matrix is singular. So by using this method, let me be looking for the coefficient of the polynomial that provides the minimum squared error when comparing the polynomial curve to your data point. Okay, so actually, dear friends, the least square method is generally used to fit polynomial to large set of data points. So the idea is to try to design a model that represents some observed behavior. Okay, so now how we are just going to solve it? Of course, the same x point, that is a point. So see here, the same a point, and towards the same b points, we have just taken the coefficient matrix, and we are going to apply, okay, using least square method. You can find a solution for the coefficient a0, a1 and a2 that provides a parabola that minimizes the squared difference between the curve and the data points. Okay, so let me just observe what is the p point first of all. So here we just have the a0, a1 and a2. And dear friends, of course, here you can calculate this least square solution of the problem, okay, which takes the coefficient matrix and the vector with the independent terms as here as an input. And this exact least square which just provides several pieces of information about the system, including the residuals, rank and singular values of the coefficient matrix. So in this case, you are interested only in the coefficient of the polynomial to solve the problem according to the least square criteria, which are stored in the value p. Okay, so now let me just even considering a linear system that has no exact solution. So this exact least square that provides the coefficient that minimized the squared error. So by using this plotting, so let me just observe what it has. And dear friends, here we are just making use of the matplotlib. Okay, and here you are creating a numpy array named x, and with the values that is rearranging from 0 to 1 containing 1000 points. And you can also create a numpy array named y with the corresponding values of the module. So let me just plot the curve for the parabola obtained with the module given by the points in array x and y. Okay, and here we are giving that exact points 1 and 5, 2 and 13 and 2 and 25. So let me just plot 8 and see the node thing. Okay, so notice how the curve provided by the module, tries to approximate the point as well as possible. And dear friends, you can also use the same thing. One of the alternative is using a pseudo inverse is also that. Okay, so another way to compute the least square solution is by using the which we just say more precious, that is inverse of a matrix. You can think of this pseudo inverse as a generalization of the matrix inverse, okay, as it's equal to the usual matrix inverse when the matrix is not singular. So here I just give you the same thing which it just gives you. Okay, and here again I take what is the a and b, and let I make it here. So this is what my a and b, and I just go for pseudo inverse here. Okay, and inverse of A. Okay, now here I just go for P2 and let me just have the P2. And yeah, dear friends, this is the same similar code from the previous which we have just given. And yeah, one and only thing, same approach used to solve linear system with the inverse of the matrix. You calculate the coefficient of this parabola equation using the pseudo inverse and store them here in this P2. Okay, and here the least square here. Kindly, even though you can just see what is there in this P inverse, pseudo P inverse. So see here, this is the exact way, because actually A is a square matrix, and here P inverse will provide a square matrix with the same dimensional of A and optimizing for the best fit in the least square sense. And however, it's worth nothing that you can also calculate P inverse for non-square matrix also. Okay, you can also make it use for non-square matrix also. Kindly just make it something in any real world applications and make use of an hands-on exercise. Okay, and yeah, if you need any particular in such a case, yeah, kindly just put it in the comment box. And yeah, dear friends, of course, I think you have we have discussed how to use some linear algebra concepts with Python to solve problems involving linear models. And of course, we have discovered that vectors and matrices are useful for representing data, and that by using a linear system, we have also made a model practical problem for that, solving them in an efficient manner. And hopefully, I think this exact video would be very much useful. And of course, we have also discussed by using determinant and solving a problem using matrix inverse. And here we also included interpolate polynomial to fit a set of points by using this linear system. Yeah, dear friends, kindly just if you are not yet subscribed, kindly just subscribe the channel. And yeah, if any of your friends or colleagues or persons who are in need of this particular video, kindly just share them. And hope so many videos we are just going to explore more and discuss a lot. So put a subscribe and like this. If you like this video, kindly just put a like onto that. And if you have any doubts or if you need any particular point to be noted or to a point to be included, kindly put it on the comment box. And see you in the next video, dear friends. Happy learning.